Sounds like
Okay,
it's,
cool.
I got the message.
Yes.
All right.
Okay.
Excellent. Hello, everyone. Thanks, Hugo. So we did a lesson last week. It was a travesty because we lost, Hugo lost connection, and he's really the leader of this class. I'm his teacher, and we're partners in this effort to help people understand linear algebra better. So we're redoing that lecture with more material that I think will be more helpful. And we know a lot of people are watching because they had to study for tests and stuff this weekend. But thank you for all that are joining live or on the recording. And we hope these are clear. And I want to explain something to you. I feel a little frustration for you because we're learning some things, and you may be thinking, that seems really cool, but how are we going to apply that? And how would I do that particular problem with more complicated numbers? Hang in there. We're going to get to that. And at a certain point, you're going to have several big ahas all at once. And then we'll go through more of the same kind of stuff. And then you'll have yet more big ahas. So right now, it's kind of like we're studying bricks that are a new type of brick, and they help you build buildings faster. And then you think, well, yeah, that's a cool brick, but let's build something with it. Well, we're studying the different types of bricks you need to build this building, because you need a corner brick, and you need the regular bricks, and you need the half bricks so you can go around windows. And so I'm making a silly analogy, of course, but it's very close. So we want to be able to define an equation for a plane in 3D space, but let's go ahead and think ahead. We could also define a line in 2D space. What are we saying? We're wanting to be able to define a subspace in any space. So for example, if we're in R4, well, we'd like to be able to define a cube in R3. We'd like to be able to define a cube in R4. And it could keep going. But what's the value of that? It gives a unique power to perspective. But even if we never found a case to use it, understanding the mechanics we're going to use, that's going to serve you really well. So let's look at this case. We've got some column vector A, and we're going to do the dot product of it with 3 points in R3. And we're going to set that to some constant D. Okay. And then A is looking like this: A1, A2, A3. So they do have to be the same dimensions or the same number of elements to be able to do the dot product. And if we do that all out by hand, it looks like this. Well, what we're saying is that all of this defines the equation of a plane in 3D space, real number 3D space. Now, you probably remember, you've heard, it takes 3 points to describe a plane. And on my LinkedIn post, it was beautiful the way someone described this. I said, well, it takes 3 points, but if you know a vector normal to that plane, that is A. A is a vector that's normal to the plane. And so A dotted with any X, Y, and Z in that plane will always equal some scalar D. Now, I want to let that sink in a minute, because that's powerful. Wow, I can define a plane or a subspace, and I can define an R to the n minus 1 subspace in any R to the n space. For any point in that space, I can define a subspace. And we're going to do some examples to make this more clear. So you either need 3 points to define it, to define that subspace, in our case, this plane, or you just need one normal vector. And the way that brilliant woman put it, she said her teacher gave her this when she was studying this. You go. Ah, good. Okay. We had a recording blip. It was just a blip. Uh, you go, just let me know you're there.
Okay, I think I should just make you the host. So that this doesn't happen again. So let me just do that right away.
Well, I still need you to let me know on Slack or LinkedIn that we lost each other. Slack, I've got it right open to your message so you can let me know, but I'm also seeing the participants. So I'll see if you drop off again. Okay, but the cool thing is now, well, what does 3 points look like? That's what this case is down here. But let's say we don't know the normal vector, but we know the 3 points. Well, if we have 3 unknowns, which in our case are the elements of the normal vector, A1, A2, A3, and these 3 points times that vector, with each of these rows is going to be dotted with each of these elements to give D. That's how this works. We haven't gotten there yet, so sorry for this, but when you see this, we have a 3 by 3 matrix times a 3 by 1 matrix or vector. And when you see 3 by 3, 3 by 1, the inner dimensions have to match. So when we do that, though, it's this row times these elements, so it looks like this. And then, but for x, for point 1, that's why these ones are here. And for point 2, it looks the same. We just subscript each of these with 2. And for x3, it would be the same. Just subscript each of those for 3. So don't let that confuse you yet. But if we didn't know A1, A2, and A3 yet for the normal vector, if we at least have those 3 points, we can solve for this algebraically. Now, you may be thinking, oh, but Tom, what if it was R 20,000? Yeah, we're going to learn how to do that. And not just with the libraries. You're going to learn how to write your own code for it. And it is super cool. Trust me. All right. So we've got it either way. We either know what the normal vector is, and I keep skipping it. It's like if you have a color palette, which is a plane, you can either support it by hanging it from a string, or you can support it with 3 points. And it's a beautiful illustration because that's exactly what's going on here. When you look at a stool that's on 3 legs, that's a form of a subspace in 3D. But when you look at a hanging table, just hanging from its center, it's supported too, and that's the normal vector. Assuming it's hanging from its exact center, center of mass, that is. So we can get that either way. Now, because this has to be true, this equation has to be true for these set values of A1, A2, and A3, and for any values of X, Y, and Z in 3D space equal to D. This defines a plane, but because of that, if we wanted to just make a grid of X, Y points, we could do some algebra, and I probably, you know what, I'm going to fix this right now because I don't like that. We don't want to call that capital D. We want to call it little d because it's always one scalar. By big D, I might have confused you to think I meant a matrix. So I don't mean that. It's always D. Well, the cool thing here is look what we can do. And if I'm solving for Z because everything else is known. I'm just creating a grid of X, Y, and I'm finding out what the last point is. Well, I could have flipped this around. I could have isolated X. I could have isolated Y. But let's take some special meaning here. D divided by A3 is just the Z-intercept. And if I had isolated all this for X or Y, D divided by A1 would have been the X-intercept, and D divided by A2 would have been the Y-intercept. So with all of that in mind, before we go through an example with this, I want to show you a simpler example in R2. So that the subspace in 2D would be a line. And so we simplify all this down to this form. And so, but what do we choose for A1 and A2 is what I'm asking here. Well, let's just say it's just a vector normal to the line that we want. Let's say we want to define a line. Okay, great. Well, what if I want a slope of 1, the normal to that line is the vector -1. Remember, it's got to be perpendicular. So here's the line. And if the normal points this way, I can go -1 in X and +1 in Y. Well, what is the value for D? Well, if we know a Y-intercept, a Y-intercept, if we solve for Y in terms of X, and an X-intercept, if we solve for X in terms of Y, we can do it either way. But here's what ends up being the Y-intercept. If we just do all this algebraically, in other words, I haven't put in the numbers yet. I'm just using this equation, and I'm saying, okay, I'm just going to let X be the independent variable. And so the coefficient on X is A1 over A2, and then that Y-intercept ends up being D over A2. Well, let's see 3 examples of normal vectors and Y-intercepts. So I just define these on the fly so we get a sweep of different slopes. So if I go off -2 and up 1, now I want y'all to, and I say the Y-intercept is at 1, well, I've kind of gone ahead and forced everything a certain way. But we'll see how we work that out. And then if I want the Y-intercept to be 0, but I want the normal vector to this line to be -1, 1, well, that should be 45 degrees. I think this is, well, we'll figure out the angles. And then this is a lower slope because it goes out only 1 and up 2. But you'll see it. We're going to draw these out. Okay, so how are we going to do that? We'll create an empty vector of, I got to remember what I meant by these. Oh yeah, this ended up being the slope and the Y-intercept 0. This ended up being a slope of 2 and a Y-intercept of 1. And this ended up being a slope of 0.5 and a Y-intercept of 1. -1, that's why the M is there. Okay, so I'm just creating these empty arrays, and then I'm going from -6 to 6, but I'm just creating my points ahead of time now. So as I go through here for I, I'm gonna get tenths of a point, of a whole number that is. And so for each of these, this is the slope of 1, and then I'm just incrementing. So this is the equation of a line. Y equals the slope times X plus 0. So that's the Y-intercept. Then here's the slope. And again, the X plus 1. So that's the Y-intercept at 1. And then 0.5 times X minus 1. And I hope y'all can picture in your mind's eye what those are going to look like. So what am I doing down here now? I'm saying, okay, for an X limit of -6 to 6, etc. And I think I changed this, but I did, but we'll look at it here in a minute. I just want to do the plot, each of these plots. Now, I've just compressed it. This is not PEP8 valid to do what I've done with the semicolon. It works, but it makes your code harder to read. I don't normally code this way. I'm just doing it so we can see more and less space. And I also did it for a LinkedIn post. But notice that we're plotting X and each of those Y's that we created up here. We're just feeding in those vectors, or those arrays, excuse me. Then I'm doing an arrow that's normal to each of these lines. And so each of these, okay, the recording stopped, and I'm going to see, Hugo, it looks like you're still there.
I am.
Okay,
It's just
good.
my bandwidth is a mess. It's a big mess.
Oh, I understand. You know what, Hugo, I think, I mean, we can talk about this later, but I think I need to go ahead and get my own Zoom account, and then we can, I do have good bandwidth, so we can do that next week.
Okay, that's fine then. Let's go.
Okay, we'll keep going.
So, but I've made you the host right now, so you won't get that recording stopped message.
Okay, no worries. But we do need to get this recorded somehow. Maybe you and I can do that independently. Okay, well, now I'm going to just look at those. Now, remember, these are those arrows, and you really, we found in the past, we really need to do this parameter for the arrow function in Matplotlib, which is length includes head. So, but it's not as crucial here because I'm not even making sure these normal vectors are unit vectors in this case. I'm just showing that indeed they come out that way. And by doing this algebra up here, by defining those normal vectors first, like we did here, I was just saying, if I do this calculation and set the value for D, well, really, I was kind of going backwards, actually. I said what I wanted for, oh, you know what? That's just for this specific case here. So what I want to do, in fact, I think I did, y'all probably saw it, and you should catch me on it. If I'm going to solve for that the way I did, this has to be a negative. So let's fix this. Boy, I was being sloppy there. Okay, because let's think about that. I'm isolating for y. So the first thing I'm going to do is subtract a1x from both sides. So the first thing I get is a2y equals d minus a1x. And then the next step is divide both sides by a2. And that's how we get this part, everything divided by a2. So that was a good catch. Now let's see if I got any other problems. So that meant that I also left out there that this should be m, and we're going to ahead and use that. No, we're big boys. We know that, and girls, we know that mx is a multiplication. So, but in this case, what we're saying is we want to force the y-intercept, this d over a2, to be 1. And if we set this as the normal vector, that's how we get those slopes. So let's just look at that real quick. If we've got a -2 over, a -2 for a1 over 1, then of course that gives us a slope of 2. And if we have a -1, that makes that a +1 over 1. We have a slope of 1. And we're going ahead and saying that we'll have a slope of, a y-intercept of 0. That's what we want d to be, is just 0. So you actually get to define d too, so you can define where your line's going to be. And then we have +1 over 2, which gives us a slope of 0.5, but we want the y-intercept to be at -1. But we're choosing each of these to be our our normal vectors. And I might have fudged those a little bit. I scaled them. So this first one, I divided them both by 2. So that's -1, 0.5, and this is totally kosher. And negative 0.5 and 1. So I just scaled these two by dividing that vector by 2, because we're just interested in direction for this normal vector. And as you can see, the first one's got a slope of 2, and here it crosses the y at 1. Here we cross the y at 0, and this has a slope of 1, but we're going off in the normal direction from there. And here we're crossing the y-intercept at -1, but we have a slope of 1/2. And there's our normal vector. Well, that was just a crawl before we run example. Oh, let's see, what was I doing down here? I was just doing some stuff with Plotly. I'll put all this in the notebook, the main notebook. Let's go back to the other notebook. Okay, so let's just extend what we were seeing. We were talking about, oh, I either need 3 points. Each of these rows is 1 point in 3D space. That's if I don't know the components of the normal vector yet. And if I don't know what D is, but, well, we would actually have to define a value for D. But once we do that, we can solve for the normal vector for any D. And again, if we're just creating, again, this has to be valid for all points in R3. So we're just going to create a mesh of XY points, a grid of points, and then we're going to divide all that by A3. And like I said, again, D divided by A3 would be our Z-intercept. So again, we'll just do a very simple problem. We're going to go in ahead and define 3 points this time. And they're going to be 1 on the x-axis with 0y and 0z, and then 1 on the y-axis with 0x and 0z, and then 1 on the z-axis with 0x and 0y. I hope I said z-axis here. And then if we just say we want D to always be 1, then clearly A has to be 1, 1, 1. And that means that is a normal vector pointing equally along x, y, and z out from the origin. Well, if we solve for that the way we talked about above, z just equals 1 minus x minus y. And let's see. So basically, when x and y are 0, z should be at 1. Now let's look at how to do that. I'm just going to do this really simple. I'm going to go from -20 to 21 because range doesn't include the last point. I'm going to step by 2, and for each of those, I'm basically going from -2 to 2 by dividing by 10. So I'm storing my x, my y, and my z. And this is just, oh, okay, I don't know if y'all can see Caleb, but he's big as a Shetland pony and he wants outside. So give me 1 second. Let's go. Sorry for that. Oh, my God. There you go. Come back. Actually just wanted love. I wanted outside. Probably going to interrupt me again. This is just the size of the points we're going to use in a scatter plot here soon. But you can see we've created this grid. So we've got a lot of -2s while we step y, and then toward the end, we're all the way to 2, and we're still stepping at y. So x changes real slowly. There's a lot more points in between, as you can see by these indexes for the points. But then you can see how the z's go from 5 to -3, etc. So we've created a data frame because the plotting routine I'm going to use likes to receive data frames. And then we also have to, we want to plot, so we understand this, that line, the normal vector. So it's just from 0, from the origin out to 1 on each of these. And we're giving it, excuse me, the same labels for X, Y, and Z. And we've put that together in Plotly Express. Now, in case you guys are new to Plotly Express, and frankly, I'm kind of new to it too, but if we want to combine graph objects, this is the trick. We say figure 1 equals this scatter 3D that we're about to look at, and figure 2 equals this 3D line. And then we can define a third figure where we use this graph objects module that we've aliased as GO, and we just say dot figure, and the data equals figure 1 data plus figure 2 data. So that's how you get away with that. Now, this is going to be a little hard to see. I apologize for that. If you don't want it to zoom in and out while you scroll, you do something like this. But watch what happened here. Oh, and you can get the controls up here just like this. I'm going to do an orbital rotation. And it's hard. I'm sorry, I'm in dark mode. I can see these colors real well, but this is X and it's got these labels Y and Z. And I'm going to start rotating this, and you can see the normal vector because it was pointing straight at us. But if we look at this plane like right on its edge and we start twirling that very slowly, and I'm trying to stay controlled here, you can see how it's always normal. Isn't that beautiful? So we just created a lot of points for our plane, and they were controlled by that equation. And then, but we could have defined it with this normal vector ahead of time. And actually, yeah, but this time we solved for them, but it was easy to solve for them. So yes, in fact, A is the normal vector. So let's test another case. And this one's going to be even simpler. So ignore this stuff. I found I didn't really need it. But if you like to do dark mode like me, this is very helpful, this statement. And you will all have access to this notebook. Okay. Now, because we're doing, and let me get something different open real quick. Oh, shoot. I may have to go, well, we'll look at it here first, and then I'll go open a better version of it. Matplotlib 3D plotting is great, but there's some things we really want to look at. And you can't look at them in a notebook, unfortunately. But if you follow this code, these are the imports we need. And then let's just step through this first, and then we'll go look at it in a Visual Studio Code output. We'll control it there, and it'll open up a new window for Matplotlib so we can rotate this 3D plot. So we just establish a figure, and we establish an axis, and we're only going to have one plot. So that's why it's all ones here. And subplotting in Matplotlib, we haven't gone over that yet, but we will soon. I'm just going to ask you, if you want to do one 3D plot, this is a good way to do it. So, but we have to add this, and even the documentation recommends doing it this way, where we've got this as an add-on to this. In the documentation page, they recommend that. So I did cheat a little. I try not to use NumPy too much or use it the other way, but we did the other case above where we created a grid of points, but I just got lazy. And so this is a way to create a grid of points really fast. And so notice where I've got XY here. Well, if I separate out the X, it's like this. And if I separate out the Y, it's like this. And what I'd like y'all to do on your own is play with NumPy mgrid and do it for the case where you just have one of these, and when you have two of these, and look at the difference in structure so you can understand, oh, Thom needed X two-dimensionally and Y two-dimensionally, and then he calculated for Z, and that's exactly right. But notice I have to fill up a, forgive me. So, by the way, this is just meaning create 21 points from -2 to 2. It'll include 2. Why is it 21? Because if we have all digits, 1 through 10, both positive and negative, we also have the 0. Well, that means we have 11 points, including the 0. So that's why this is also 21 by 21, because we're calculating it for each of those grid points. And because we have X and Y and we're creating a grid, I'm just separating them out. That's all I'm doing here. And then that one line is 0, 1. And then we've got two commands here. We want to plot a surface, and then we send in our X, Y, and Z. And this is just the type of color map we want. This is one of the options for a color map, import CM. And then the line width, I didn't want line widths for the grid of the surface. And alpha, this just is the degree of transparency. If this is 1, it's no transparency. If it's 0, you can't see anything. So if it's like 0.2, it's just very hazy. And then we just do some labeling for the title. And by the way, totally reuse this stuff in your other stuff. Don't feel like you always have to go study all the documentation on Matplotlib to start using something like that. As a good friend of mine put it, a coder I really respected, we all suck at the teats of Stack Overflow. You know, that's where we get our milk, or Geeks for Geeks, or someone's blog post, or someone's GitHub. Try to understand it deeper and deeper over time. But we're just trying to get the job done, and that's okay. But this command right here, set box aspect, is very important to being able to see normality to the plane. And you can see that doesn't look normal, but it is. What's happened is Matplotlib's taken liberties to scale this z-axis visually. So yeah, we can look at it, but we have to believe that it should have been normal. Now, we'll come back to this, like I said, in another way, but let's do another simple and obvious equation of a plane where we're using Plotly again, and then we'll go look at that somewhere else. So what am I saying here? Here's 3 points. If I go out, if I'm at X equals 1 and Z equals 1 and Y equals 1 and Z equals 1 and X and Y equals 0 and Z still equals 1, well, that's just a flat plane lying above the XY plane at a height of Z equals 1. And so we're going to say all of that equals 1, too. We just want to, that's how we're going to constrain it, is with this value of 1. Well, that yields a normal vector of 0, 0, 1, which makes sense because it's a plane perfectly parallel in 2 dimensions to the XY plane, where Z is 0. And so now we create our grid of points in the XY plane, and our equation for Z simplifies to 1. Z always equals 1, no matter what you feed in for X and Y. Well, let's just plot that in 3D. I'm just repeating what I did above. And of course, I didn't need to put this. I put it for clarity to match this up here. And then, well, I'm going to go ahead and extend that normal line through the plane. Really, it should touch the plane. But look, here it is, the same thing we did above. And now I'm looking at that flat plane above X and Y. So you see here, this is X, Y, and I've gone to where we're looking right at the edge of the plane. And as I twirl it, that normal vector stays perpendicular all the time. Okay, now give me 1 second while I go find our, okay. Oh, I should show you all what I'm doing. So in my cloud drive, I have this main directory I called ACT. And in mentoring, I have linear algebra. So I'm doing this in in Linux. This is a Linux file manager, and I'm going to open VS Code. And so I'll pull this file manager back out of the way. It's not screen review, and I'll make this bigger for you guys. And we don't need all of this right now. So just make this, let me know if I need to go, I'll go one bigger just to be safe. But again, you can, well, I guess you can't watch the recording now, but at least it's in the notebook. And this is the same code I just showed you in the notebook. Again, we should put that comment here too. I will go over here to get that comment again. We'll go up here. And I just want to copy this comment. And we're going to go back to our VS Code window and just, okay, great. Now, I will run this. And there it is. Now, that line that didn't work in Colab, yeah, but works here, was able to make it so that all these axes are on equal visual scale. And you can see now, if we get right on the edge of that plane, as close as we can, and I start trying to rotate all of this, oops, you see how it stays perpendicular, no matter how we look at it. Now, this, I can't emphasize how huge this is. You may be, you may be working on a specialized problem someday that no one's created a module for, and because of your knowledge of linear algebra, you can completely come up with a novel solution because there wasn't a Python module for it. There wasn't something in sklearn or any of that. Now you just know how to do things. Well, Tom, has that ever helped you? Absolutely. That post I did on the dot product of two vectors over the product of their magnitudes equaling cosine theta. And basically, you didn't need to worry about cosine theta. It's just like, well, cosine theta, when the angle between those two vectors is 0, that means they're exact matches. But when they're close, excuse me, when they equal, that means theta is 0 and cosine theta is 1. But even if cosine, if the angle is really close and you've turned the text of documents into numbers by, we can go through an example like that so that you can say, well, how can we use what we've learned so far? Well, you've already learned enough to do some amazing things. And I can tell you this, having knowledge of linear algebra has definitely helped me out of a clinch multiple times. So now one thing, and maybe y'all could take this as a personal homework assignment. It'd be so great if we plotted one dot by adding another scatter plot. Let me do this. We added another scatter plot to what we're doing. I got to keep this open to keep the plot open. But okay, see how we did this plot surface? We could do a scatter 3D And just add that point of, oh, when X and Y are 0, in other words, wherever this crosses the plane, we want to create just one dot there. And, and that way it's just easier to see where this intersects the plane. If I hadn't added this alpha, and this is a weakness to Matplotlib in 3D, if I hadn't added this, it would be harder to see. And this looks a little nicer, but we could have made this scatter 3D also. All right. Are there any questions? And you can do them in the chat too. I've got the chat open. Okay, now while y'all are thinking of a question you might want to ask, I'm going to take the stuff from this notebook and add it to the main notebook that we've been keeping. And if you want, I'll show you how I do that. Okay. I click on this first one. I'm hitting Control, click, click, scroll down, click. But every time I click, I'm holding the Control key, which also gets the outputs. And then I right click, copy cells. I'm going over to our main notebook. This is important to y'all because you're going to make copies of my notebook and extend your work, hopefully. At least that's my hope. And we're going above where we started here with the R3. And I haven't figured out a different way to do what I'm about to show you, but I'm just creating this new block. And then I'm doing a Control V, put all those cells in here. And then I go back up to delete that one block. Okay, I didn't hear any questions. So I hate to assume that that means everybody understands this perfectly, but that's possible for some of you. But I just need to reiterate this over and over and over again. If you're too shy to ask a question and you really have a question, please just ask me or you go privately. If you go can't handle it, you go pass on me. But I don't want y'all to be afraid. The person that asks a question right now because they're a little confused, you're probably going to help a lot of people by asking the question. It could be that someone thinks they really understand this, and your question helps them realize, oh, I hadn't thought of it that way. And that's an important question. And that happens to me a lot when I hear other people's questions. So this is a safe place. We're not being recorded right now. So please ask away if there's something that is unclear.
The whole session is recorded. It's on YouTube.
Oh,
I always have two.
Good.
Yeah, I always have the two of them, the two options: recording on YouTube and recording on my local computer.
I didn't realize that. I'm glad it's still being recorded. That's
great.
Yeah,
it is.
But now YouTube can't see the chat. So if y'all just give me feedback in the chat one way or another. Let me know, like, oh no, it's clear, Tom. Thank you. I don't know how to apply this yet, but I think it could be really cool, and it definitely could be. If imagine you are in an interview for some type of oh, hang on one second. My oldest son's playing stuff in the background. He forgot I was teaching. So you're in an interview for some computer visualization job. Could be gaming, whatever. These normal vectors to a surface, and imagine this surface isn't flat, then it's defined by gradually changing normal vectors in different directions. Well, this stuff's hugely important that way because that is a very economical way to define that surface is with this equation. And then the computer's got to go and create a bunch of little triangles that mesh together small enough to form this smooth looking surface on the computer screen. And you might be thinking, well, why is a subspace important? For the same reasons, because the computer can only give you a 2D rendering of the 3D. So it's a matter of perspectives. And so this is like very foundational steps to understanding a role like that. Even if there's routines to do these normal vectors to the surface, change them, you still need to know how to come up with the math to smoothly change the direction of each of those normal vectors, because each place on that plane, each dot on that plane, that curved surface is going to have a different normal vector. And so being able to define those normal vectors is important to the artificial lighting that shines and many, many other things. So this stuff is huge. And I think personally, if you're a little lost and you just go through Saul's lectures on this again, and go through this latex, and then LaTeX, and then go through other things, go through the code, and just keep thinking about it. Over time, it'll go, oh. And even if you don't get it completely, get it enough, move on with the material, but just keep trying to see the bigger picture of how you can actually apply this. And there'll be no end to the ways you can apply it. I think, now, Hugo, is this clear to you? Do you have any questions?
I've done part of this last week, so I
Yeah,
reread the notes.
You've seen it twice now, so
yes.
you're probably doing good. Now, I'm going to call on some friends here. Noro, is this clear to you, buddy? And you can answer in the chat or coming off mute. Either way, it's up to you. Okay. Well, if it's been clear to everyone, I'm happy. And I hope it was super helpful. The notebook, let's see, all I need to do to make double sure. The notebook is up to date. And now, let's see, I'll go ahead and drop its location since it's handy here. Just copying the link. You can all view it, but if you want to work on it, you'll need to make a copy of it, which is totally fine. If you end up teaching from it, I just would appreciate a mention. I don't want y'all to feel like you can't use this. If you were to go help a group understand this stuff better, but give me, if you're using some of my material, give me some credit for having taught it to you. But yeah, I guess we can break off early, have an hour break before we join for Albert and Ketke. But I'll give y'all, I'm going to just declare this time over. Hugo's going to stop the recording and I'll hang around for any questions. And then Hugo and I will have a talk at the end. So I really hope you guys found this helpful and clear. And I think we'll move next into cross products. So Hugo, let me know when you stop the YouTube.